Dear student, today I am going to discuss on a very important topic on round robin scheduling algorithms. This scheduling algorithm is very important from the university perspective, and it is being covered in almost all the universities question papers. As the name indicates, round robin is almost all like a ring structures, as I have shown over here, and it is more or less a resemblance to FCFS scheduling algorithms which you have studied at the earlier, that is first come first serve. In the similar fashion, round robin is also performing. This particular scheduling algorithm is a preemptive process scheduling algorithms, and this is having a peculiar characteristic is that this type of algorithm is designed only for the time sharing systems. Apart from this, another important component is that each process, we will having a process P1, P2 like this up to Pn. Each process is provided with a fixed time to execute. You can say fixed time to execute, and such time is called as quantum time, or we can put it in short QT. So if it is more than the quantum time, what happens is that CPU will exit out. That means CPU will not able to process it. So that is the one of the importance of the QT. Suppose if the QT is equal to say 1 second, if P1 is let us take 4 seconds. If P1 need to process, when it comes to the CPU has to process this P1 process within 4 seconds. Otherwise, the P1 process will exit it out. That means CPU cannot exit do executions more than the given time, which is QT. In the context of this one, you will see that in the average wait time under the round robin policy is quite long. Whenever we calculate the average WT, in this case it is still high. Otherwise, this particular scheduling algorithm has more or less similar structures just like a FCFS. Now let us see how this particular round robin algorithm is going to work out based on the problem. Now let us put some questions in these structures with the certain PID, and based on the PID we will calculate the Gantt chart, that is the Gantt chart area, and also we will calculate the wait time, average wait time and average turnaround time, just like as we have seen in the earlier discussions. So let us put the questions such as the different process. Say we will take a 4 process, P1, P2, P3 and P4 process, and each process is having arrival time 0, 1, 2, 3 with the burst time 10, 4, 5 and 3. Now in this case, just like in the FCFS, we don't have a priority, so I cancel it off. Now we know that here QT is equal to 3 unit, as the question itself indicates. So we'll first start with the Gantt chart. So we will see that the first process P1, as it appears in front of the CPU at 0 arrival times. So for the first process we will put in the PID based on the PID in the Gantt chart as a P1. When the P1 process first arrives, it arrives at 0 interval times at the arrival of a P1, and this process has to process based on the 3 unit. Now here, like as you might have referred to my series of earlier video slides, there we used to consider a variable times, either 1 or 2, like that. But here we cannot do the variable because here Qt is a fixed. You have to remember that time sharing system is a fixed based on Qt. This is very important to understand. This is fixed. So you cannot take a 1 or 2. So fixed Qt times you have to keep. So which is equal to 3 unit. Now based on this 3 unit times, we have to calculate the P1. Now as you know, it is a preemptive. Preemptive means the first process will go for a 10, then the next process will go for a 4, the other this one will go for a P3 will go for a 5, and P4 will go for a it will go for a 3, and this will go for a 5, this will go for a 4, and this will go for a 10. So as the process keeps on moving, so if we should not allow the P1 to run for a 10 units and in the first instance, rather we have to take care of the other process. So what we will do, we will go with the 3 units. So if we go with the 3 units plus 3, so it will be 3 at the executions. So the remaining time is 10 minus 3 is 7. Now if you see that 3 means what? 0, 1, 2 and 3. That indicates that all the 4 process has already arrived. That means our ready queue has reached here itself. So this is ready queue. So that means the whole process has attained here in the ready queue systems. And what happens after ready queue? You are aware about it. Here another thing is that even if the process, when we need to go from one process to another process, we have to see that how the distribution of the process is there. Now the next process we will consider is P2, because as per the arrival times the next process is 2. Now burst time is 4, but we cannot consider whole 4 because of the 2 conditions. One is Qt plus another is that it's a it's a preemptive. Preemptive means it will able to allow the CPU to go in an interval process for the executions. So here we have to consider the Qt with respect to Bt. That means Bt minus the 3 unit will give the Bt as 1 in the process P2, and here we will add 3, it becomes 6 here. Same things we go for the next process. So next process is P3. So in the P3 what happened is that here also we have to go from 5 to, because at a time we cannot process 5, so 5 minus 3 is 2, so here plus 3 it becomes 9. So after P4 is what? The next process P4. P4 is what? 3 minus 3 is 0, so it is plus 3, so it becomes 12. Now after P4 is what? It goes in a cycle. So it is going like it started from here, then it goes back like that cycle. So we will go in that particular order, and so we will put here as P1. So what is P1? From 7 minus 3 is 4, so plus 3 is nothing but 15. After P1 is which process? P2. But what is the burst time of P2? It is 1. So since it is 1, so we no need to put 3, so we will add plus 1. So that is 15 plus 1 is 16. Now after P2, so that means this has gone to 0. So we have two processes into 0. So after this P2, which is the next process? It's a P3. So P3 is a process, is how much? 2. So our Qt is 3. So we need to add 2, which is a 80. After P3, which is that this 3 process, then it is a P1. So P1 is a process. Either we can write like this one, or we can do, but we have to go in the same order like a Qt. So P1 is that 18 plus 3 is 21, and after P1 again the next process will be minus 3 means it is 1. It is 1. So after the again the same process P1 will come, and here we have to add plus 1. That is, it is going to give you the value 22. So you have seen that it is just like FCFS, but only the thing is that we have to consider based on the condition of Qt the same thing, and not only FCFS, FCFs under the primitive conditions, non-primitive conditions and the primitive condition, both we have to consider together. Now here another important component you have to understand is that all the process running time has come to 0. So once the all process is 0, we have to compute for the CT. So let us view the CT from from these directions. If the CT, if you try to see, the first process is P1 from the right side. So it will need a 22 unit times to complete. Now after P1, before ahead of P1 is what? Is P3. Just before that one is P1, that we have to ignore because P1 here. So just and before P1 is P3. So P3 is how much? Here it is 18. So we have to consider the 18 is the completion times of the P3. Now once the P3 is also considered, then we have to look for the P2. So P2 is 16. Now after P2 is over, now what is remaining? P4. So P4 is here, so which is 12. So we have covered everything. Now time arrival, turnaround time is 22, that is CT minus 80, that is 22. Here it is 15, 16 and 9. Waiting time is turnaround time minus BT, that is equal to 12, 11, 11 and 6. Now we sum up every combinations, and we will find the average waiting time. Waiting time is 12 plus 11 plus 11 plus 6 divided by total number of processes. There are 4 processes, so that one comes as 13.25, and average turnaround time is equal to our 22 plus 15 plus 16 plus 9 divided by total number of process 4, and we will get around 18.75. So this is the one of the problem related to the round robin scheduling algorithms. Here certain important parameter is there, which I will discuss in the subsequent round robin scheduling algorithms. Thank you.